So any questions from the last class?
The last class was pretty simple. I mean, that's what I felt. It was the simplest of all, is what I
Yeah,
felt.
because it's kind of like a new algorithm, and so decision trees are relatively simple, but the more complex we get into, like pruning and deciding the depth of the tree and stuff like that. But the coding of the algorithm is again going to be the same model, but understanding different parameters of the algorithm is uh, is somewhat important. So today, actually, I think today's class will be a little more complex. I'm going to talk about artificial neural networks,
Okay.
and so yeah, we have a lot of, and I'll give a basic intro into deep learning
Okay.
today. If at all one class is not sufficient, we can actually extend this to the next class also.
Okay.
Next class, I'll talk about how to use tensor flows and stuff. So I'll tell you what, I mean, I won't get into details about convolutional neural network and recurrent neural networks, but I'll give you a brief intro as to what they are, because
Okay.
that is a more advanced thing. We'll start with the basic neural network today, what a neural network is and how does it work, and stuff like that. Satya, do you have any questions from the last class? Was that decision trees was relatively simple, right?
Yeah, it was pretty clear.
Okay. So today I just wanted to, I will start with neural networks. So this is again, can everyone see my screen?
Yeah, we can see us.
Okay.
Yeah.
So basically, right, like why? So we have so many algorithms and we have like supervised algorithms, non-unsupervised algorithms. But why this particular branch of or section of study has grown multifold is there's a reason to it. So no matter like, so let me just show you the basics. So this neural network is not something new. It's been basically published, I think, long time back, like 4 or 5 decades back. People have been using this, but somewhat it never had an opportunity to scale, because it's really difficult to train the neural network. It reads and requires a lot of computational power, and we didn't have enough data before. So now neural networks, especially, so neural network is the building block of deep learning, which everyone is going after. So nowadays, because of the abundance of data which we have, and the increase in computational power, the leverage of the cloud, right? Like nowadays, you can parallelize your process, get umpteen number of machines on the cloud to run your clusters and stuff like that. So it's becoming very easy to actually program and deploy neural networks as a service. In fact, if I were to pick one algorithm or one thing you want to learn in supervised learning, so these are all good things to learn. Okay, and in decision trees, random forests, naive Bayes. So we'll still cover a lot more. I mean, we'll still cover a lot more in the future classes. But the more important, or like if I were to pick one machine learning algorithm for teaching supervised learning, it would be neural networks. So so how many of you heard what deep learning is? It's been it's been thrown around a lot these days. Like everyone is working on deep learning, and deep learning has become like an integral part of data science now. So everyone actually like you pick any problem, like people use deep learning, any complex problem, right? Like for example, Alexa, the way Amazon Alexa, how the way it answers questions, right? Like when you ask Alexa, what's the weather today, everything has deep learning models behind it. So even if you take the most complex of Google Brain or this thing, they use like deep learning behind the scenes. So deep learning has been like in the last 2 years at least, deep learning has taken a very serious foreground role, because we'll talk about how deep learning models are built and why it is working so well. But that's why I said, like, so if I were to pick one algorithm for supervised machine learning, I would pick neural networks. And eventually, when you use a bunch of neural network, it becomes convoluted neural network, and that's what deep learning is all about. I'm going to talk about what deep learning this thing is, but let us start with the basic this thing. So The reason why neural networks became famous, especially in the past also, is like if you have this problem. How many of you heard what an XOR problem is? Anyone know what an XOR problem is? Or like I think if you have actually did like logic gates in college, what is the XOR operation?
Or neither, or it's not of or something, right? Is it or?
No, it's basically so a XOR or XOR problem is basically represented as this. So operation is if it is 0 and 0, the output is 0. If it is 1 and 1, the output is 0. If it is 1 and 0, the output is 1. If it is 0 and 1, the output. So this is the XOR operation. It's called so it only becomes, so generally an AND case, like it's different from AND because 1 and 1 is always 1, right? 1 and 0 is 0. So AND OR operations, so you're familiar with what OR does, AND does, stuff, right? So XOR is a problem which is basically which actually becomes 1 when both the inputs are different. So if both the inputs are same, then it would become 0, and if both the inputs are different, then it is 1. So what happens in this case is just waiting because Raghav had some questions on this. Anyway, so if you actually plot these XOR problems, right? So 0 and 0, so if I take this as two classes, right? If it's 0 and 0, then I'll actually point, this will be my 0 and 0. 1 and 1 is going to be here. Let's say if this is 1 in my coordinate space, this is 1. And 1 and 0 is here, and 0 and 1 is here. So I have 4 points. I have, let's say this is my two classes, right? So first class is basically, so these two belong to first class because they are both 0, 0. And these 2 points belong to my next class because both of them are 1 and 1. So at that point of time when they actually started with neural networks, there was no algorithm which could solve this problem. How will you draw, like this cannot be linearly separable, right? So if you have points like this, draw me one linear plane which can separate these two things. Ideally you have to come up with a decision boundary, right? That's what you're teaching the machine. Like you have to come up with a decision boundary which can segregate both the classes. But if your data is like this, so it started from this XOR problem or the XOR problem. If your data is of the nature of what XOR is, basically there was no algorithm back in those days which could actually segregate, because whatever linear line you draw, right? You draw this line, you can't segregate both the classes into one. So because one of them would fall. So the only solution for this was non-linear boundaries. So where is this? So the only way you could solve something like this was using non-linear boundaries. That's why neural networks first grew prominence. So what is the other algorithm which we learned for solving non-linear? One of the other algorithms we discussed in the previous class.
SVM, right?
SVM. So SVM was one other thing but SVM also finds it difficult to project these two into another. So you have to play with RBF kernels and stuff like that, but it wasn't giving a clear decision boundary. Because SVM ultimately, if you look at what the crux of SVM is also a linear classifier. But the only thing what SVM does is it projects the points into its own space where these two are linearly separable, right? Because ultimately even SVM tries to draw a hyperplane, but it takes this, if you give it a nonlinear problem, it will use something called as the kernel function to project it into another space and where you can make it linearly separable. So that's why SVMs have grown. Like in fact, when I was talking about SVMs, I said SVM and neural networks are the two main algorithms which supervised machine learning produces good results. But now, because of the complexity, after this lecture, you will know like why neural networks or deep learning has taken off to the levels where it is today. So one main problem what neural networks can solve is it can actually draw a decision boundary which is like this. which is maybe I drew it really close to. Let me draw it again. It can actually draw a decision boundary, which is like this. So anything within this, anything which is inside this boundary is considered class 1. Anything which is outside the boundary is considered class 0. So it started off with the XOR problem, and then to solve this XOR problem is when they started developing a neural network. So
Sorry, Sankalp.
yeah,
I joined late. Are you explaining the decision tree algorithm?
no, I'm explaining today. Yeah, last class was decision tree. Today I'm talking about neural networks,
Okay,
artificial neural network.
okay.
So
Thanks.
today we'll talk about neural network, deep learning, and like how neural network is built. So this class is going. I'm thinking it might be a long class. We'll go slowly. If it is, if not, if we don't finish it in this class, we'll extend it to next class also, because the main thing we'll learn today is perceptron, neural network, activation functions, back propagation, feed forward networks. So it's a very involved class. So did you have any question?
No, I just joined late, so now that's
Okay.
why
No.
I'm muting myself.
No worries. So today's class is on. I mean, if you look at my previous slides, it's on artificial neural networks. So today we'll start with the basic neural network, and then we will extend to see like how it is. Like the topics which I spoke of, we'll talk about most of. So generally, my style is not reading from PPTs, because you can even read that offline. So I want to spend enough time to like explain the concepts, and then we'll go through the PPTs, and then that'll be like a revision for you. So okay, so the reason why neural networks or artificial neural networks was initially invented was to solve problems which are non-linear in nature. The main problem, or the paper, if you look at the first neural network paper, it actually said we can solve the XOR problem or XOR problem. XOR problem is this thing. So when you have points with 0, 0, which is one class, 1, 1 is one class, as you can see, these are like opposite to each other, right? So you cannot basically have a linear boundary which can separate them. But neural networks actually, we will see, it could actually come up with decision boundaries so it doesn't project it into another space. It doesn't do anything. Given the current space, it will come up with a decision boundary which can actually segregate, and it can draw like really complex boundaries. It can draw boundaries like this, because it depends on how the neurons work. So neural networks are primarily used for solving like non-linear problems. You can even solve linear problems also, depending on the activation function you use. We'll talk about what activation functions are and stuff like that later on. But let's go into, so before I go into like what a neural network is, let's talk about neurons, like how human brain works. So this neural network function was actually developed by this guy who actually studied the human brain quite a bit. So the human brain. So 1 second, there's a question on the chat. So when neural networks draw a decision boundary, how does it make sure it doesn't overfit the data, because the line is segregating it pretty well? This is a really good question, Satvik. I would ask you to just bear with me for a few slides, because there are something called as hidden layers, and there are something called as pooling layers, convolution layers. I'll talk about it later on, and we will see why it won't overfit the problem. So there is something called as early stopping, where we don't learn it too well, but just hold on that thought. I'll cover that overfitting problem in a bit. So before we go into the actual neural network as such, so how does human brain works, right? If you know, human brain or even the nervous system consists of, I think, like billions and billions of neurons. So if you see what a neuron is, it has something called as synapses. I won't take like much of the, I mean, you can learn it much better in biology class. But then the concept of how I'm just drawing something which looks like a neuron. So what happens is, these are like the nerve endings and stuff. So whenever so don't don't quote me. My drawing skills are really bad. But what happens is when in a neuron, you basically have something simulating you, right? When, let's say, if someone takes a needle and pricks you, your brain suddenly, let's say you're sleeping, right? And then someone takes a needle and pricks you, your brain suddenly reacts and you wake up, right? So what is happening there? This particular thing is the neuron. It has a huge tail called synapses. So what this does is it takes something called a stimulus. Stimulus is anything external, right? Stimulus. So if someone pricks you, so basically that particular signal travels through your synapses layer and goes to a neuron. And the neuron basically gathers this information, and it basically has certain threshold. So for example, right, like you take a, like let's say if you're sleeping, let's say if someone basically takes a feather and just, not tickles you, but just rubs a feather against your hand, will you wake up? Most of the time you won't, because that stimulus is not enough. So every neuron has some threshold. If your stimulus is above the threshold, stimulus is above that threshold, that's when that neuron triggers. It triggers, and then basically it activates and then passes that information to the next neuron. So there are like billions of neurons in your whole body. So something which is basically pricking your hand is passed through different neuron. That this is connected to another neuron, and then that's ultimately it comes and reaches your brain. So the idea behind this is whenever some external stimulus comes, it basically travels through the synapses layer, goes to your neuron, and there is a certain threshold. If it exceeds that threshold, it passes that information further. So this guy who actually was studying this, like the human brain, was like, what makes the decisions in uh, for humans, right? It is the human brain. He wanted to build an algorithm which works exactly like a human brain, and that's how the whole name neural network. Neural is basically coming from a biology term. So the idea behind this is, what he said is, let's say if I take a, so I have a stimulus and there is something over here. This is basically having a threshold. If this stimulus exceeds this threshold, if this stimulus exceeds this threshold, then we will say that this neuron is active and it passes this information further. So this is the whole concept behind a neural network. So in a neural network, what happens is this stimulus can come from multiple locations, right? It can come from, like, there might be like hundreds of neurons connecting to this layer. So this is how, like, the human, like in the human brain, there are like billions and billions of neurons which actually simulate a particular neuron. So the idea is basically, when you have this stimulus coming from different sources, it'll come, and then this particular function will actually sum all the stimulus together, and then we just check if this particular stimulus is greater than the threshold. If it is greater than the threshold, then you pass that, you pass that stimulus further. If it is less than the threshold, you just ignore it. So a classic example of that is basically, as I was saying, right, like, not all of, you don't react to each and every situation in your day-to-day life. Let's say if you're focused on something, like, sometimes there are small things in which you won't react to. But if someone, like, drop a hot mug of coffee over you, the stimulus for that is really high, and then the higher the stimulus, if it passes the threshold, that thing passes to the next level of the neuron and finally reaches your brain, and that's when you get notified of things. Like, a small example which I gave you was, when you're sleeping, let's say if someone just puts a feather on your hand, you won't notice that, because the stimulus produced by the feather is not enough for you to, like, generate that level of signal for you to wake up. But if someone takes a needle and pricks you, that produces so much of stimulus that it exceeds the threshold, and that information gets passed on, and ultimately your brain will be notified of that particular stimulus. So let's actually look at how this guy actually put it into a neural network form. So the basic fundamental unit of a neural network is called a perceptron. So what perceptron, so this whole thing, so A neural network consists of a number of perceptrons. So you can have like 3 or 4 perceptrons and that will become like a neural network. But a basic perceptron is pretty simple. So you basically have some inputs. So you have x1, x2, x3. These are your inputs. And then you pass it to something called as an activation function. So this is your perceptron. The perceptron has these inputs. This is inputs. And then the perceptron P has something called as an activation function. What is an activation function? Activation function is nothing but what we saw there. Activation function is basically the function which tells you beyond which threshold should you actually pass the signal further. So each of the stimulus is or each of the input is weighted. You have a certain weight for every input, because every stimulus is not going to have the same weightage, right? Like a feather can have a different weight, a needle prick can have a different weight. So if you look at it mathematically, what this perceptron, this whole model perceptron does is this is an activation function. So this whole thing is called a perceptron. So what it does is it takes W1 x1 plus W2 times x2 plus W3 times x3. Now this is basically your input. And what did we actually look? We actually come up with some threshold, right? If this is greater than the threshold, then we say, it's greater than the threshold. Then we say we pass this signal further. If not, then if it is less than it, then the value will become 0. If it is greater than it, then your Y output will be the same as this thing. So this is exactly how neurons work. So this particular model or perceptron is basically modeled off a neuron. There's one additional factor which every perceptron has something called as a bias. So this is always going to be there irrespective of whether you have input or not. So this is the bias term. So let me just erase this. So ultimately what we have is W1 x1 plus B. So this whole thing is going to be your input. So every perceptron has a bias, which is like the basic input which is always there, like that, irrespective of so that's like irrespective whether you have the input or not, you always have a certain bias or a certain weight which is associated with every perceptron. So this is the whole model of how a perceptron is actually modeled. So this threshold, how do we determine this threshold? This threshold is determined for something called as an activation function. So activation function is another term which you will keep hearing in the later on of the lectures. What activation function does is, it's basically like there are 3 main activation functions which your current perceptrons use. There's a sigmoid activation function, there is a tan H activation function, and there is ReLU. If you actually read or if you actually see a lot of data science papers, or if you see most of the algorithms these days, they use this thing called ReLU. I'll tell you why ReLU is actually more better also. So it's called ReLU. ReLU, it stands for rectified linear unit or something. I will talk about like each of these activation functions later on. But for example, a sigmoid function is something like this, right? So 1 plus 1 plus e to the power of minus x. This is a sigmoid activation function. So what this x stands for is this input. Whatever input you are actually passing to your perceptron, that is basically plugged into this, and then you decide how much is your this thing. So if you plug it into e to the power of this x, whatever, so this whole thing is going into this x here, and then you decide if this is greater than, so if this is greater than like 0.5, so you have a threshold here. If this is greater than 0.5, then you say please pass this output as it is. If it is less than 0.5, then you say it is 0. So what is the importance of this activation function, right? So ideally, let's say we don't have any activation function. So we have something like W1, X1. Let's say I don't have any activation function. W2, X2 plus W3, X3 plus B. I can just put a threshold on this, right? I'll say, hey, is this greater than some value? Then pass it, or else make it 0. Do you see any difference between what this input is and what this is? Can you tell me what is the nature of this particular activation function? So the question I'm asking is, why do we need activation functions? Why don't we just directly take these inputs and say, hey, if these inputs are greater than some constant threshold, then I'm going to basically pass it. If not, because that's also what a neural network does, right? Like ideally what a neuron does is basically takes all the stimulus it gets and sees if it is greater than some threshold, then you pass it, or else you say it is 0. So what is this activation function adding? If you look at the nature of the activation function, can you say something about the activation function?
It's like a logarithm function.
It's a logarithm function. It is based. So this is one such. So this is this is sigmoid. ReLU is basically another function which is greater than 0 and 0 if x is less. 0 if x is less than. So I'll talk about ReLU and everything later on. But what this activation function is adding is the non-linearity aspect of it. So basically, if I clear all, let me clear all my drawings. So let's look at the sigmoid function. How does it look? 1 plus. So ideally, I said this value is nothing but what is this value? W1 x1 plus W2 x2 plus W3 x. This is for a 3 if it has 3 inputs plus B. So that is the x which goes into this. So if you look at the output y, if I actually plot, and let me call this value as x, right? If I plot my x and y together, this function looks something like this. It basically adds this non-linearity aspect of it. So how do you convert your input which is linear? So remember when I said it can draw boundaries which are like this? The reason it can draw boundaries which are like this is because of these activation functions. These activation functions are actually non-linear. So like for example, sigmoid is like this, tan h is actually, it's somewhat similar, but then the reason people use tan h is because it will pass through 0. This doesn't pass through 0, right? Because you can see is 1 by 1 plus something, it can never be 0. So the use of the activation function is to basically give a non-linear, to introduce non-linearity between your inputs and outputs. So for that reason, we use these activation functions, which are currently used in a perceptron. So is this thing clear how a perceptron works? A perceptron is nothing. What is a perceptron? A perceptron is nothing which takes inputs and a bias. So it has 1, 2, 3. It has, and then it has something called as an activation function. That if the criteria satisfies the activation function, if it is above the threshold, it will pass that signal further. If not, it won't pass it further. So this is what a perceptron does. Any question on any question on a perceptron? I just showed how they modeled a perceptron from looking at the human brain. So your output y is equal to x1 w1, so it has some weights, x2 w2 plus x3 w3 plus b, if it satisfies that condition. Any questions on perceptron? Okay, if there are no questions, then a neural network, I'll talk about what a neural network is. So a neural network consists of a bunch of perceptrons connected in some manner. So you have one perceptron, like this whole thing is one perceptron. You connect it with another perceptron. Let's say you have two perceptrons, right? The output of this is again y value, right? So P1 and P2, you connect it to another. So you can create different networks with a neural network. So you can actually add some more weightage to this. So this will actually work as another perceptron layer, right? You have weightage W3, W4. So you basically add weights to the outputs of each perceptron and pass it to another perceptron. So you can actually create like multiple connections like this, and everything is connected, and then you pass it further. So there are different kinds of neural networks you can create with how you organize your perceptrons. So now all this is good. So how is this useful to me? Because I actually, what do I have? I have a bunch of features and I have labels, right? So you're teaching me all this, but how can I model my machine learning model using these bunch of features and labels, and where do I plug these things in? So that's what the whole neural network does. So what the whole neural network does is basically each of your inputs, x1, x2, x3. So it need not be that you can have one perceptron. As I said, a neural network consists of number of perceptrons. Let's say you have 6 features. There are x1, x2, so on up to x6. These are different features. So I can create, sorry, this is x. And what is your y? In general, y is your label, right? It's either 1 or 0. If you're doing a 2-class problem, it's 1 or 0. If you're doing like 3-class problem, you'll have 1, 0, 0, 1, 2, 3, 4, like depending on number of classes. This is your y. So y is basically your labels. So the way you can actually create a neural network from your training data is by training this thing. So you have x1, x2, x3 as in one perceptron, x4, x5, x6 in another perceptron. So now I'll create 2 perceptrons. Google is sending me ads also. Okay. So I create one perceptron. The properties of the perceptron are these weights, W1, W2, W3. And then this has an active. Let's say I use sigmoid activation function here. And I have one more perceptron. I use ReLU here. ReLU as activation function. This is W4, W5, W6. The output of this, I'll give it to another perceptron. So the output of this is input of the next perceptron. In this, I will use like a tan. I'm just giving examples. Tan H activation function. So this is, let's call this Y1 dash and Y2 dash is the output of this, and it has another weight, W7, W8. So the output of this, if everything satisfies together, this is your class. So basically what you will train is the output should be your class label. Ultimately, output is your class label, because it is adding some weights and then it is actually manipulated. So in general, right, what we do for these in the data processing step, each of these features are normalized. So they are between 0 and 1. All of them are normalized. So like, because of, like, let's say for example, we have age as the feature for the Indian liver patients, right? So what we do is min-max normalization. So if we know that 65 is the maximum age of the patient and 22 is the minimum age, so what we do is we take each value, subtract the minimum, and then we actually divide it by maximum. So this is what is normalization. So this way we actually do this. So this is a min-max normalization. What we are saying is artificially we'll make this value 1 and this value close to 0, and everything will lie between 0 and 1. So we have to normalize all the vectors because your ultimate output should be 0 or 1. So you have to manipulate this W, your weights, such that the inputs when you give, your output is either 0 or 1. So what is it learning in this process? Or what is it that the neural network can change? So these inputs are constant, right? So when I'm saying the output has to be either, output is nothing but the label, your label Y. So when I'm saying that the output is either 0 or 1, what can you change in this neural network to give you this output? Any ideas? Did everyone follow like how I drew this perceptron? Like I just used 3 perceptrons. First perceptron takes first 3 features. Second perceptron takes next 3 features. The outputs of each perceptron is given to the third perceptron. And the third perceptron's output is basically going to be my label, which is 1 or 0. So what is it that this perceptrons, or what is the training in this? How can you ensure that whatever you give here, output will either be 0 or 1? Because I can give, let's say I give 0.1, 0.2 and 0.3 as my features, right? How will the output be 0 or 1? What are the parameters this perceptron can change? Any ideas? I just showed you the equation, right? So what can you vary in this perceptron such that your output is 0 or 1?
X1, X2, X3.
No, X1, X2, X3 are your features, right? You can't change the features. So what can you change?
The weight. Also,
The weights.
bias, is it?
Bias and weights. So the things which the perceptron learns is this weights. W1, W2, so on up to W6. So these things are what are the parameters and the biases. So the weights and biases what the perceptron learns, such that, so you've given one input and you say that my output is 0 or 1. So ultimately the way, so that is what is, so now we will talk about back propagation and stuff. So how does it learn this thing? Basically it starts with some random weights. Let's say it'll just randomly pick a weight. Let's say my first weight is 0.2. My second weight is 0.3. So, and let's say you give these weights, you first give in your features, and for simplicity's sake, let's assume that they pass the activation function. So your what will y1 dash be? Y1 dash is nothing but, it's going to be, I said it passes the activation function, right? It's going to be a summation of all wixi's plus b. And then your output over here will be this multiplied by this weight W3. Oh, sorry, W7. So this is multiplied by W7, right? All these weights are multiplied by W7, and then you have another set of weights here multiplied by that by W8, and you get your output. So this is output has to be 0 or 1. So initially you won't get an output 0 or 1. Let's say you get an output of, let's say 0.3. But in your training, you're saying that, hey, no, this has to not be 0.3, this has to be 0. So you basically calculate your error. Your error is you are supposed to get 0, but you're getting 0.3. So you say that my error is minus 0.3. So based on this error, it does a process called back propagation. So that's very important in neural networks. It's called back propagation. Back propagation, what it does is it takes this error, changes the weights, and then recalculates it. So before I go into like the details of back propagation, I just wanted to give you a brief understanding of like what the neural network can change. The neural network basically changes these weights such that your output here matches your label. So once you actually give in all your training data, for all the training data, it learns these weights. And then it comes with the optimal set of weights such that it is 0 or 1. The number of times it basically learns this thing is called an epoch, which we'll talk about it later. But is this thing clear? Is this clear as to what it is doing? It's basically, it has to change these weights such that your output should either be 0 or 1. So if it is not 0 or 1, it starts with some random weights. And then once it actually learns these weights, it goes and finds out what the error is. And using a process called back propagation, which we will talk later on, we are going to basically learn, okay, if the error is 0.3, then we will change these weights accordingly. We'll change this way. to minimize the error. So from 0.3 you have to become 0, right? You'll change these weights accordingly and then recalculate recalculate your metric again such that it actually comes to 0. So this process of calculating it and then getting the output is called feed forward. It's called feed forward neural network, or this is forward propagation. The concept of taking the error and then coming back and retraining your weights is called back propagation. So I just wanted to introduce what back propagation is, and now let's go to the slides. I mean, it's all explained in the slides properly. But is this thing clear as to what a neural network is and what it is doing? Any questions on this?
Can you just summarize this for FF and back propagation?
Yeah, I'll do. So basically, let me clear everything. So I actually drew a network which has 3 perceptron. So I'm actually creating a neural network. So is everything clear about a perceptron though? Any questions on perceptron, like what it does, or like what are the concepts of a perceptron? Deepika, is a perceptron clear?
Yeah, perceptron, that all that is clear. Just this back propagation.
So I actually am so this is my exercise. I have to create a neural network which takes 3 perceptrons. So first perceptron is here. It takes, so I have 6 features, right? X1, X2, X3, X4. I have another perceptron which takes the other 3 features. So this is P1, this is P2. So this is X1, X2, X3. It has its own weights. So the weights are part of the perceptron. That is something the perceptron changes to match your output. And every perceptron has certain bias. So this is X4, X5, X6, and it has its own weights. W1, W4. It has its own bias. The output of this is given to another perceptron. This actually is a third perceptron. I'm saying the final output has to be the label. So given these features, the label, like the label is the class property, right? It's, let's say if I'm taking a 3 class problem. So there are 3 classes, like I'm trying to classify the features of apples, oranges, and mangoes. So either the label is 0 or 1 or 2. But when you're training the data, you know because it's supervised learning, right? So you know what the label is. So what feed forward or forward propagation means? So forward propagation is the concept of calculating these weights, the aggregation of these weights with the bias, seeing if it passes the activation function, and then the output what you get here is is called the forward propagation. So given some weights, you will basically take the summation, right? So the input for this perceptron is summation of Wi xi plus b. That is the input to this perceptron. And let's say if this perceptron has some activation function, and let's say if it passes that activation function, then the output here is also going to be the same thing, right? So the output here is going to be, so the output here is going to be what the activation function applied here. The activation function applied here is 1 plus e to the power of minus x. So the output of this is basically going to be 1 plus e to the power of minus this value, whatever this, I call this as x dash, minus x dash. And now that will be the input of this thing. So this will have another weight, right? Another weight is W7 and W8. So the input to this is W7 times this value, W8 times whatever value you're getting output here, which let us call this as x2 dash. X2 dash is again 1 plus e to the power of minus summation of Wixi, where I is 4, 5, and 6. And then you calculate this W7 times this input, W8 times this input, and then the output you get is basically that. The calculation which is going from the inputs to the output is called forward propagation. what is back propagation? So I said the output has to be either 0, 1 or 2. But how, you cannot actually ensure that these values are 0, 1 or 2, right? Because you need to know what weights you need to determine to make the value 0, 1 or 2. So if you actually come up with some random weights, so let's say I initially start with some random weights. I use random weights and I calculate this. The output I get here need not actually be 0, 1 or 2. Let's say the output is 0.7, but it belongs to class 0. So what I'll tell the neural network is, hey, you know what? You're giving me 0.7. Change your weights. So now go back. So that is the back propagation. Back propagation is the concept of changing the weights such that you have to get the label as 0. And how do you actually what are you propagating back is the error. You are getting 0.7, right? But what you actually have to get is 0. So what is your error here? I mean, you can calculate error as actual minus expected. So your error is 0.7. So using this error, you'll say that you'll propagate. I'll show you in equations how that happens. You propagate this error backwards. So now you will say, hey, change W7. Don't use W7. So instead of W7, use W7 plus some delta W. This is my new weight. The process of calculating these weights depending on the output is called back propagation. So back propagation is you first get the output using forward propagation. You get whatever value it is, then you calculate the error. Now let's say your error is basically, it has to be 0, but you're getting as 0.7. This error is now back propagated such that you change these weights and then you recalculate, because if you have new weights, now you recalculate it. It'll next time when you get, it'll be close to, maybe it'll be like 0.2, because you calculated one set of weights, but it still has some error, right? Because it's not 0 yet. Now next time I'll propagate this error 0.2 back, I'll recalculate my weights again. So the concept of, so the way the neural network works is it goes forward, it goes backwards, forward, backwards. So each of this iteration is called an epoch. An epoch is
trial and error, right? Trial and error.
Sorry?
It's trial and error, right? It's test it out, change the weight, again go back, test it out.
So first one is trial, but the next one is not trial and error. Next one, you are actually going to change it based on your error. So if higher the error, you will change your weights even more. You will understand that when I cover it in the slides. What back propagation? Let's say if you have let's say your output is 200, right? When you're label, so you won't get an output 200 because you're normalizing these things. So these things have to be normalized. So everything, all the data for which you give it to the neural network has to be normalized. You're right. Initially, it is trial. Initially, randomly, it will determine the weights. W1, W2, W3, it will give randomly. But from the next iteration, it is not going to be trial and error. Next iteration, it is going to be with the weights are changed depending on what your error is. If your error is really high, let's say if your error is 2.2, then you will change the weights. So you will actually reduce. So let's say I've chosen a weight of point. You'll see that when I do the example, I randomly chose 0.8. When I chose 0.8, this value is really high. So now, depending on the error, you will take, I'll show you like what the math is. Depending on the error, you will change this particular value such that you will get as close as possible to 0. So I wouldn't say the second and third is not trial and error. The second and third is depending, you propagate this error back. The higher the error, the higher you will change the weights. The lower the error, the lower you will change the weights. Is that clear? The concept of propagating this error back into my neural network is called back propagation.
Yeah, that's right. That's correct.
Back propagation. So now let's look at, everything is there in the slides. We'll go through that again, but I like to draw these things and show you like what. Then we will talk about how these weights are changed and stuff. But when I'm training a neural network, okay, to summarize before we go into the slides, firstly, a basic unit of a neural network is called a perceptron. And what are the properties of perceptron? Perceptron has inputs. You take the weighted sum of those inputs, because that's how our neurons work. neurons take like inputs from different, because every neuron has different endings, right? Like if you look at it, like it has different nerve endings. So from all the nerve endings, it will take the simulated input, it will sum them up, and it has certain bias, and it will put that to an activation function. If that activation function output exceeds certain value, we give the output of that activation function to the next perceptron. So similarly, so that's basically a perceptron. A perceptron takes the weighted sum of inputs plus bias, uses an activation function. If that activation function exceeds a certain value, then you pass that new value further. If it is not, then you give 0, then it won't activate. So that's a perceptron. The next thing is a neural network. A neural network consists of a bunch of perceptrons. You can arrange it any way you want. You can have one perceptron connected to 10 perceptrons, or you can have two of them connected. And let's say in this case, if I want to add 2 more perceptrons, so I can add one perceptron here, which takes this input, another perceptron directly to this. So it all depends on how you want to create your neural network. A neural network is a combination of perceptrons in which you basically give the inputs should be on the very end. So this is your input to the neural network, and your output should always be the label of your class. And how do you match that these inputs will give you that output layers is because it will change the weights. The weights and the biases are something which the perceptron changes every single time. So the process of calculating with random weights, it will calculate, each layer will calculate its output, and it will go further. Ultimately, you'll get one value. This process is called forward propagation, because you're coming from here, you're going forward. But once you come here, you know that the value you get is not equal to your label, because these are random weights. So you will get an error. So using this error, you will go back and change your weights. You'll change these 2 weights first, and then you will change these 3 weights first. We will see that in the example clearly. But you will change these weights, and then afterwards you'll calculate the error from here. You'll change these weights. You'll change all the weights. So now the concept of propagating the error back to the weights is called back propagation. After you do back propagation, you have new weights. Now you again do forward propagation, because you have the same. So again, you actually have now you get your new this thing, right? Now you get your new set of input data. Then you use that input data, calculate with the new weights, and then go here, find its label, then you calculate its error, you come back. So you basically iterate it n number of times such that your error here, final error, is minimal as possible. So next class we will talk something called as the gradient descent. That is what we use in this case to calculate the weights. But overall, did you understand what back propagation is, what forward propagation is, what perceptron is, what a neural network is? Any questions on this? What is an epoch? I just mentioned what an epoch is.
It's like the iteration from going from feed forward to back propagation.
Yes. One epoch is one forward propagation plus back propagation to forward propagation. So one iteration of the weights and everything is called an epoch. So basically, if I say I'm using 10 epochs to train it, that means I'm going backward and forward 10 times. So you'll have 10, every epoch will give you different set of weights every single time. So I think that's enough of like me drawing this thing. Let's look at the slides now. So when you look at the slides, you will basically, all right. So having said that, so I actually drew a basic idea. Now it will be easier for you to follow the slides. Chat message. How does the machine know that the output belongs to a corresponding class? Like how does 0.7 belong to 0 and not class 1? So Satvik, so is the question clear? I think he was asking, how does the machine know whether whatever output so let's say I got 0.7, right? Why am I subtracting it with label 0 and not 1? Does anyone know the answer to this question? Basically, Satvik is asking, How does a machine know that the output belongs to one class and not to the other class? Like, why are we subtracting 0.7 from 0 and not 1? I'll let someone answer this question. But everyone has this question as to why I'm subtracting it from class label 0 and not 1. How is it that I'm knowing it is class 0 or 1? Anyone wants to guess?
Does it maybe do it because it has the lowest error with that class?
No. So I think I missed the main point here, right? So this is training data. So when I give the set of so what is training data? So two things. One, this is training data, and second, this is supervised learning. So what the first fundamental thing in supervised learning, what we do is every observation is given the class label, right? So when you're training the data itself, you're saying that, hey, first set of x1 to x6 is basically belongs to class 0. Like if you look at the Indian liver patients, or like let me look at the Indian liver patients. So I think maybe I took that for granted that so first and foremost thing, we are doing supervised machine learning. Supervised machine learning means what? Supervised machine learning means in the training data set, you give a certain observation and you say that this belongs to class 0 or this belongs to class 1. So if you don't know the data, then it's called unsupervised learning. And neural networks can't work on unsupervised learning algorithm because in that case, you don't know whether to subtract from class 0 or class 1 because you don't know what it is. But in supervised machine learning, you basically always are given the data. So let me look at video games. So let's look at like Indian liver patients. So Satvik, is that question clear? So here I know what the value. So again, don't get confused between. Until now, we did only one algorithm which was non-supervised, which is k-means. In k-means, we try to determine the class based on how the data is projected in the space by forming groups, dynamically forming groups. But every other algorithm so far, we actually have determined it based on supervised machine learning. Because now look at this thing. Now this is an observation. So these are my features: x1, x2, x3, the ones which I was drawing there. I said 6 features. Let's say we have 10 features, right? The first thing which we do here is normalize this data. If the age is between 65 to 22, we normalize the age between 0 to 1. So 65 is given the value 1, the minimum is given the value 0 or like 0.1, and we normalize the data. So once we normalize the data, these are the set of inputs which we provide to the neural network, and we tell it that, hey, this particular observation, it belongs to this label. So it either label 0 or 1. So when I give this observation, your output should be, in this case, let's say your output is 1. And let's say by choosing random weights, it is giving an output of 2.2. Ideally, I should get 1, but I'm getting 2.2. So I subtract 2.2 from 1. Satvik, is that clear? Like, we are not guessing what the label is. We know what the label is. That's why it's called training phase. In the training phase, you know what the label is. Once the training phase is done, what does that mean? Once the training phase is done, we now don't change the weights at all. The weights only change during the training phase, such that your input observations will give you the label which you are expecting. And what you're expecting is what you're providing to the neural network.
Yeah, that's clear.
So it's not that we are guessing that this particular observation has to belong to so yeah, that would be unsupervised machine learning, and neural networks won't work for that. In most of the cases, you have supervised machine learning. Unsupervised is very rare cases where, so clustering is the only unsupervised machine learning algorithm which can work, because when you form or when you project them, you form groups and you see that they can be separated through the groups. But in every other case, we have the label for it. So you take this observation, the output label you need to get is 1, but you are getting 2.2. So you subtract 2.2 from 1, you get that error, and then change the weights. How you change the weights, we'll look at it in the slides, but you change the weights using back propagation. And then now you recalculate it with the new weights. Now you see that it is still not close to 1. You again calculate the error, again change the weights. You keep doing that. That's called epochs. The number of epochs is again a parameter to your algorithm. Tatvik, is that clear?
Yes.
I think he doesn't have. Doesn't have a microphone. Okay. So let's go forward. Any questions on like apart from the details of how the weights are determined and stuff? Any questions on perceptron, neural network, bias, epoch, backward propagation, forward propagation so far? So I'm assuming it's. So again, you have to tell me whether you have questions, because if
it looks very easy, but after some time it's easy to forget.
But then we'll do exercise. So we have like 3 programs.
Yeah. I mean, when you explain, it looks like very simple and straightforward.
Yeah, it is supposed to be simple and straightforward. But then when I talk about convolutional neural networks, recurrent neural networks, you will understand like how it is like, like how. So again, like the coding aspect.
As long as it's going in flow, it looks very easy. But as soon as you will ask some question from the middle, totally blank.
No, that's why I'm asking questions.
Yeah.
If you understand it properly, then you won't.
Yeah.
Then it'll trigger the neurons in your brain also, right? The back propagation happens in your brain. So it's, if you look at it, that's how even we look, right? So when I ask a question, that's basically an error between your understanding and my question. So then you will go back and think, oh, okay, what am I doing here? Like, why am I not? So you basically change the weights in your neurons. And then once you learn something, so it's exactly like how a brain works. That's why they call it neural networks, right? So, I mean, this is a good example I can take. When I ask a question and you don't know the answer, that's the error you have. So basically, you have some predetermined weights. And now you back propagate that question. Now learn the new weights, and now you have the answer. Now I have one more question. Yeah.
Does it mean like new weight means higher concentration in neuron point of view?
New weight means it is giving more relevance to that particular feature. As you can see, every weight is associated with one feature, right? X1, X2, X3 are features, and every weight is associated. So after you train it and you look at the weights, you will understand which features are given more importance and which features are not. So that is another way of like so basically the whole concept of, so for neural networks, you need not even do all the PTA, all that stuff, because it'll automatically, if you train it for enough epochs, it'll automatically learn that these weights are important, these features are important, and these features are not. Now, I think Sathvik asked a really good question last time, that how do you ensure that, we spent a whole class on overfitting and underfitting. How do you ensure that it doesn't overfit? So it depends on the number of epochs. So if you actually give like infinite epochs, it will overfit the data to what your features are for every this thing. But if you actually, so there's something called as early stopping and stuff. We'll learn that later. So as long as your training accuracy is not like close to 100%, that means that you have not overfit the data. And how do you control that overfitting is by, you specify the number of epochs you give to the algorithm. So if you say that I only have 5 epochs, 6 epochs, so generally we train for like 100 or 200 epochs. So we keep changing the number of epochs for it to learn, not to overfit the data. Okay. So now let us go into what the actual neural network is. So neural network is basically, it tries to mimic exactly how the brain works. And if you look at back propagation, all these things it's exactly how our brain also goes. When you basically learn something new, that means your weights in your head for that particular topic change. So, like for example, let's say if you're thinking about movies and you're actually having this class, right? And then you're obviously distracted. And let's say if I ask a question, you don't know the answer to that. That's because you have a higher weight in your brain for the movie section part. So then when you go and you're then focusing on this thing, you're reducing the weight for movies and you're increasing the weight for maybe like machine learning and stuff. To give an overall gist, that's what happens in the human brain also. That's the process of learning. So this is called active learning, the whole concept of these epochs and this thing, because after every output you're learning and you'll change the weights. Again, you will give an output. Again, you'll change the weights. The number of iterations what go through is different. And if you want to now understand what a bias is basically how every brain is different. Like some people are really sharp, right? Some people, they can understand things really well, so they actually have right number of biases in their head. But some people, they actually need like 2 or 3 iterations to learn. They have smaller biases. So the way they model this particular neural network is exactly how a human brain works. So if you actually look at it, algorithms that try to mimic how the human brain works. The first algorithm used was perceptron. It was actually developed in 1959, and then it was used on spoken words for 1990. The main reason it didn't have that much success is because computational power needs to be, you need to have higher computational power and enough data, which now you actually have that. Now you don't worry about like, oh, is my algorithm taking so long to train? Now we have enough computational uh, now we have enough computational power to like train the networks within a day at the max. So if you actually look at, so ImageNet is something you guys should take a look. ImageNet is this database which has like a lot of classes. Like it's a central report. Look at the database. Sorry, look at the databases which are there, which are open source and available. ImageNet is one database. If you go to ImageNet, you will find like a lot of data with labels. So you have horses, all images of horses and say it is horses, all image of cars and they say it is cars. So everything has a label to it. So every year there's a competition. So how many of you heard of Kaggle? Kaggle is this, it's Kagle, Kaggle. So if you're a data scientist, you should basically look at Kaggle competitions. Kaggle are like the standard, world standard. So if you're Kaggle top 10, that means you are the best in machine learning. So the best brains actually compete at this Kaggle competitions. So Kaggle competitions occur every year. So in Kaggle, they have, so ImageNet is one database resource, which actually is an open source thing. So I think so there's always competition between Microsoft, Google, Facebook and these folks to actually win these Kaggle competitions. So one competition is basically every year to classify these images. So you have like billions and billions of images. Can you come up with a network which can classify these images correctly? Like I'm just talking of 2-class problem, right? But in Kaggle there are so many, there are like infinite, like a lot of classes, like that 100-200 classes. Like one class is horses, one class is cars, one class is bicycles, one class is this thing. So they run it on all this thing. So so that was recently won by Microsoft. And you know what is the neural network they used to train it? Can you guess how many neurons, perceptrons were there in the Microsoft neural network?
Maybe trillions.
No, not trillions, but they actually create. So there are different. I think one thing I forgot to mention is layers. So in my, is the drawing still there? Okay, it's all garbage. But so this is, so basically there's something called as a layer. So this is the first layer, and then this is the second layer, and then there is a third layer. So layer is basically nothing but, let's say if you have, it depends on how many neurons are connected to it. So if the inputs are directly connected to the perceptrons, then that is the first input layer. The output of this input layer or perceptrons is given to another perceptron. So that is the second layer. And then if this output is given to another perceptron, That is the third layer. So what matters is the input layer and output layer, right? All the other layers are just doing work in between. So they are called hidden layers. So that's actually one more term which we will keep using. So hidden layers are the layers between the input layer and output layer. So the Microsoft network, which actually they trained, it had like 300 input hidden layers. Each layer had around like 3,000 or 4,000 perceptrons. So you can imagine how complex the system is, right? So the the ImageNet, uh, which actually won that competition, was, so the main reason why people won't be able to train this is because imagine now I just said I just took three perceptrons and it took so long for us to go back, train the weights and stuff. Now imagine there are 300 layers in between. So that means there's an input layer which connects to another layer, which connects to another layer, another layer, like 300 input layers, hidden layers. And then you get the output and you back propagate again to like 300 layers. Each layer has 300 to 400 neurons. So imagine how long it will take to train. So for Microsoft, they trained it for, I think, I don't know the exact number, but it took them like 4 or 5 weeks to train the data. So once you train it, then they submitted it to the competition, and it did, like, until now I don't think there was anyone else who could beat that convolution neural network. So that's how. So just familiarize yourself with Kaggle competitions, look at Kaggle data sets and stuff. You will understand more about data science in general. But anyways, let us come back to like our class. So the reason why people have been working. So deep learning is nothing but if you actually use a lot of input layers and a lot of neurons, it's called deep learning. So if you use like a small neural network which has like 20, 30 neurons, it's just called a neural network. But if you actually create this complex network of like a lot of input layers and a lot of neurons in each layer, then it's called deep learning. So deep learning is you're learning everything very deeply. So that's what is deep learning called. Deep learning is nothing but an aggregation. So we will see a couple of deep learning neural networks later on. But let's go and let's go through the class first. So deep learning is now possible because of the increase in computational power. A neural network is used everywhere. There is no restriction on classification. So for example, the neural network, the game Go, I don't know how many of you play. It's a Chinese game. You actually put like white pebbles and black pebbles and play. It's a very complex game. So recently, a neural network developed algorithm beat humans in that. It beat the best player at Go because it.
Was it?
Sorry, you have a question?
Was it by Google or something?
Yeah, Google actually developed this neural network, deep learning neural network, which actually had different. So if you look at it, right, you can simulate what a brain is, right? And in fact, the best part about neural network is you can simulate how intelligent the brain should be. You can actually go and change the weights. So you can create a very smart neural network. So Google actually developed this neural network, which learned, again, it's a deep learning network, which actually beat humans in this game, because every time it learns a game, it changes its weights. So next time it becomes smarter. So it can help. So they're like, so I can't, like, if I spend applications, like what can a human brain do? Anything which a human brain can do, artificial neural networks can do that. So if you, now I don't want to like sit and like it can learn how to paint, it can learn how to paint photos, it can do 3D modelings, it can speak like humans, it can actually write emails like humans are writing. So there are different applications of neural networks. So that's why neural networks have become so popular that, so as I said in the beginning of the class, if I was to pick one machine learning algorithm which is supervised machine learning, I will pick a neural network or ANN. Then comes SVMs, then comes like decision trees, then comes for simple problems. So again, you shouldn't use a neural network for simple problems. Like if you have like 2-class classification problem, you can still use a neural network. I mean, we'll do that in the examples, but it's a simple problem, right? So there might be better algorithms to classify that. But ideally, it is basically anything which a human brain can do. This neural network can do it. So the idea is basically to, one second. So the idea is basically here to simulate how a human brain works, and using that is how we solve this neural network problems. Okay, so some of the problems is the training time. It's little slow because you have to train for different weights. You have to, but what are the main things you in your hand to select for a neural network? Like, what are the things which are in your hand? Like what are the parameters you can change? What are the hyperparameters for a neural network? Like based on what I just explained. Like if I give you the task to train a neural network, what can you change in the neural network? Like how do you configure?
The inputs.
No, inputs are fixed, right? The training data is given to you. What can you change about the neural network which will learn the data better?
Weights.
Weights is something the algorithm will learn through back propagation. It's
number
not,
of perceptrons.
Sorry?
The number of perceptrons.
Exactly. So you can change the number of perceptrons in your layers. You can change the activation function each perceptron uses. So basically the things you can change in a neural network are number of hidden layers and number of each hidden layer, how many perceptrons have to be there in each hidden layer. So those are the things in your weights and everything is I mean, ideally the question is correct. You can, but you are not changing the weights. The machine will learn the weights depending on the training data. So what can you change? How can you make a neural network smarter than the rest of the students or rest of the people is by what you can change is the number of hidden layers and number of hidden layers and number of perceptrons, and also it makes a huge difference what activation function you are using in each hidden layer. So each perceptron has an activation function. So the most popular of all activation functions these days is called ReLU activation function. That's because sigmoid and tanh have a limitation. We'll look at it when we are actually doing the back propagation example. So one of the basically disadvantages is like training time is going to take a long time. So basically that. So let's quickly go through the slides. It will be like a revision of what we have learned. So basically a neural network simulate some properties of real neurons. A neuron when fired fires when the sum of its collective inputs reaches a certain threshold. A real neuron is all or none device, which means that either it passes the signal or does not pass the signal. So there are 10 to the power of 11 neurons in every person. So you can imagine how many neurons we have. So 10 to the power of 11, I don't even know if there's a number for it. Maybe bigger than Google. Google is, I think, 10 power 10. So it's 10 Google neurons per person. So each neuron is connected up to 10 power 5 neurons. And they're up to 10 power 16 synapses. I mean, this is all the biology of how human brain works. I don't want to get into that. But as you can see, there is an input layer, hidden layer, and output layer. So input layer is basically, so, okay, now this is something you have to answer. How many neurons will be there in the input layer? If you have understood like what I've been talking about neural networks so far, you will be able to answer it. So I can change the number of neurons in the hidden layers and stuff, right? How many neurons in the input layer? I'll give bonus points to the person who answers this question. If you've understood this correctly, so input layer is basically connected to what? Okay, let me ask the question another way. What is an input layer?
The first layer wherein you give the parameters, right?
Exactly. Not parameters, but where you give the training data, right? Input.
Yeah, training
So
data.
how many neurons should be there in the input layer?
The number, at least of weights, right? Like, or the basic number of.
Okay, what is the perceptron in each input layer connected to? So when I was drawing these things, I was drawing x1, x2, x3, right? What is x1, x2, x3 there? So remember in the input section, I was drawing x1 times w1. I was giving x1, x2, x3, x4. What are those x1, x2, x3, x4?
Those
Parameter.
are inputs.
What is an input? Like, I know they're inputs, but what are they? Okay, let me give you this example. I'm giving you this Indian liver patient's data to train the neural network. So what are x1, x2?
Features.
So x1, x2, x3 are the features, right? So I'm connecting each feature to one particular neuron. So now can you tell me what is the number of neurons in the first input layer, in the input layer?
Like the number of features.
Number of features.
So the number of features in the input layer. So each feature is connected to one neuron. It is another thing that they are all interconnected with each other, but at least the least number of features, at least the number of features in the input layer are equal to the number of features, because each one is taking one feature. And you can see that they are connected to the second layer. They can be connected, like multiple things can be connected to this, but the input is going to one layer. So the number of perceptrons in the input layer is equal to, at least equal to the number of features you have in your data set, because each of them, the x1, x2, x3 are nothing but what I'm passing here is this, right? So in one perceptron I'm passing age, another perceptron I'm passing. So this is x1, this is x2, this is x3, this is x4, so on up to 10 features. So up to x10. So each of the feature is passed through one of the input layers. So you pass the number of input layers, you basically have a hidden layer. Okay, how many output layers?
One.
Yeah, you can see in the image, because the output layer basically gives you one output, right? Output is, what is the output again?
The label or the
label
class
of the observation, right? So output layer is always one. Input layers is at least equal to the number of features. You can have any number of hidden layers, any number of perceptrons there. So that's something you can control. But there's only one output layer to actually give you one label. So sometimes you can have multiple of them and then do a max mode of, like, let's say you have like multiple, ideally there should be one, but you can have multiple output layers, and then each of them predicts a label. You can take the maximum or the mode of that. Like, you can do a voting as to like which one is the highest. You can pick that particular label. So anyways, so that's how a neural network is actually defined. As you can see that this, depending on the activation function, this boundary can get as complex as you want. Instead of having a straight line, it can actually fit any particular boundary. But one of the main thing I think Satvik was asking, or he pointed out, was it is very easy to overfit also. If you actually use a very high number of epochs, it will learn it so well that it will overfit the data. So we don't overtrain it. We limit the number of epochs which we give. So let's go further. So multiple layers. So this is a cascade of neurons together. The output of one layer is the input to the next layer, and so on. Each layer has its own weights. So we have, like, let's say we have 4 features or p features. This is x0 to xp. That's p plus 1 features. So you can give your input to like multiple layers also. So here I can actually, so I take that back. So in this case, I said it should be the number of features. In this particular diagram, which I used, I was saying number of features, but you can actually have neural networks which basically can connect different features to one. So you see here, I mean, most of the cases when we train, we will actually train with the number of features as the input layer. But in this example, you can see there are 4 features, but you have only 3 layers. That's because you can connect each feature to different like all the, like this one goes through all the 3 neurons, this goes through all the 3 neurons, this goes through all the 3 neurons, this goes through all the 3 neurons. So it depends on how you connect it. Ideally, like I mean, this is a more complicated network, but ideally what I would like for the beginning cases, we would just use one per feature. But you can, so you can mix and match also, because you don't, there's no hard and fast rule like how many inputs it can receive. It can receive any number of inputs. Mind you that every input will have one weight, so each layer has its own set of weights. The output of this will again go to, so this is like a very complex cascaded layer. Like the output of this is again going through like multiple inputs to other neurons also, and finally you basically have the output, and then the aggregation is basically going to be your final output. Is this a diagram clear? This is a multi-layer neural network. You have 3 layers. You have an output layer. You give these are your inputs. Your inputs have weights. Each weight will actually, if it passes some threshold function, it will go further. The next layer again receives these inputs. If it passes the threshold function, goes further. You get the thing. For each of this observation, you have a particular label. If the output doesn't match the label, you calculate the error, and then using back propagation, you first change these 3 weights, and then you change these 3 weights, and then you change these 3 weights. Not 3, I'm sorry, there are like a lot of weights here. For every connection, you have a weight, and then you change each of the weights, and then you again recalculate. Every time you recalculate, you actually will get less and less of error. So let's take a look. So this is how it is. So basically take different inputs. I don't know what happened to this image here. This is supposed to be the bias. So the bias is here. So you actually take different inputs, you calculate the weighted sum of each of them plus the bias. So this is the aggregation of each of the weighted sum of these features. You pass it through a activation function. So this is one activation function which I'm using here. So this says that it is equal to 1 if this is greater than 0. So 0 is the threshold. Otherwise, this can be -1 or it is 0. Generally, we use 0 here, but this is an example of how the activation function works. So input, weighted input, sum of it, you pass it through activation function, and the activation function has an output. So that's how the basic perceptron actually works. So it produces a linear separator in an input space. It can represent Boolean this thing, but not. So if at all the activation function is linear, if at all this is a linear function, then it cannot. So remember I said like the activation functions which you use, sigmoid and all of them are non-linear, right? If you use a linear activation function, it can only produce and, or, and not, but not XOR, because the XOR is it cannot be separated drawing a straight line. So what produces the non-linearity of in this particular, so when I said it solved the XOR problem, what is the thing which produces the non-linearity aspect of it? So the whole neural network, what factor is responsible for the non-linearity of the neural network? I think I mentioned this when I was explaining.
Is it the decision boundary that it draws?
The decision boundary is basically, that's the output, right? That is non-linear. But if you look at it, everything is a linear input, right? Like sigma, this is a linear function here. So if you look at this thing, this is a linear function. So what is producing the non-linearity in the decision boundary? If I look at this, right, so this is basically a linear equation. So it's basically going to have a linear combination of x1, xi, something. But what is the factor which is making this boundary non-linear? Like if you go back to this slide, so this is a non-linear, right? And I said like like neural networks can actually produce non-linear decision boundaries. So what part of neural network is producing that non-linearity? Any idea?
The activation function.
Yes, it's the activation function. So activation function is the one which is producing the nonlinearity, because activation function is what, and I said I use a sigmoid, I said 1 plus e to the power of minus x, where x is that input to that function, right? So all the linear thing is actually getting into this. So the summation of wi xi is actually going into this function. So this is basically making it nonlinear. So if you actually see what is producing the nonlinearity in your decision boundary, it is the use of this activation function. So that's what this is saying. It says it cannot solve the XOR problem if this activation function is linear. Let's say if you have a linear activation function, it cannot solve it. So therefore, basically, if the data is linearly separable, it will work. If not, it will not. But then if you actually use this nonlinear activation functions, it can solve the XOR problem. So let us go into, I mean, I've showed about what, I've talked about what this thing, so that's what this is. So one possibility is if you use something like a sigmoid function, you can, because your output is a linear combination of inputs, right? But if you use a activation function, which is sigmoid, tan h, or ReLU, they actually give you the non-linear aspect to it. So as I think Deepika, you mentioned, so the activation function is what gives the nonlinearity. So and I said, right, so this is a plain linear activation function. We don't use this anymore. In fact, we don't. So one of the very high popular activation functions are sigmoid, tan h, but as of 1 year back, no one is using these two. Everyone is using this called ReLU. ReLU is this activation function. We'll see why. When I talk about backpropagation, I'll tell you like why ReLU is used and not the other ones. Let us go forward. So now this is the actual equation. So you actually have a set of inputs. Your net is basically this. This has to have a bias also. And then you pass it to this, this is your activation function. And now if this activation function is above certain threshold value, you pass that value further. So because this is a nonlinear function, right? It's an exponential function. You look at it, it'll look like this. It's not linear. Sorry, look like this. So this is what is making the decision boundary nonlinear. So tan h also is, so this is tan h. Tan h, this is tan. The reason people use tan h is because the sigmoid activation function does not pass through 0. So you can only have, if you look at sigmoid, the whole equation, e to the power of minus b, right? When will it be 0? It can never be 0, right? It's 1 by 1 plus something. So unless and until this is like really, really big, no, it can never be 0 basically, because it's a fraction. So one of the reasons why people don't prefer this is because it cannot actually have a negative bias. So it's always going to be a positive function. So people started using tan h function. Tan h functions can pass through 0. So because tan h of 0 is 0, right? So that's why they used another activation function with tan h. So now you use this for image processing also. In image processing, you basically have an image where each pixel is having some value, right? So this is a cat image. If you open any image, you will see that every pixel is a basic unit of an image. It will have some value between 0 to 255. So let's say if there's 120. So basically, the way you use neural networks on images is for each pixel, you'll create is your feature. So let's say if I have an image which is 120 cross 120, for each pixel in this particular image, I'm using that as a feature. So you'll have one neuron for each pixel, because nowadays you can actually the computational power for is really fast, right? So you can actually use as many neurons as you want. So in case of image processing, you will use one input perceptron for every pixel. So if you have 120 cross 120 is your image size, then you will use 120 times 120 number of input in your input layer. You'll use that many perceptrons because you'll convert each pixel into an image. then it will learn each pixel. So training of multi-layer perceptron. So now this is where we will talk about back propagation. So once you find the network weights, how will you find the network error? So you'll take you'll take your label minus whatever your value is, right? So you basically, so it is expect observed minus expected. So this is your error which you get. So what we do in back propagation, I've been telling you, like we change the weights, right? So this is what. So in the next lecture, I'll go into this further because this is called gradient descent. So what it does is it changes the weight based on the error. So you have an error, right? You have an error from your output label. You take the partial differential of that. So you basically see how much component of error changes when you change one particular weight. So you will then get the slope of the error versus that weight. And there is a alpha which is called the learning rate. So this is also another input parameter which you can change. So you basically decrease your weight by, I said, right, you update your weight. How do you update the weight? I said you update it based on the error. The formula you use for updating the weight is alpha, which is the learning rate, times the slope of the error with respect to that particular weight. So this is your new updated weight here. So this is the formula which we use for back propagation. So every time we actually have an error, we actually differentiate that with respect to that particular weight and then add that weight back. So I have an example. I'll show you how this weights are updated and how the back propagation goes. But sometimes you actually, in order to avoid overfitting and stuff, you actually had a penalty term. It's called regularization. We saw a similar thing in support vector machines, right? Where we actually add a penalty term to your objective function and stuff. So this is another way. It's called regularization, but I don't think we'll look into that further. But here is how you can see how the learning depends on the on your learning rate. So, or the boundaries. Here you have green and red. You see, it can draw these complex boundaries. It's not linear, but it can draw these different shapes. And then the more you give the learning rate, the faster it will come to that shape. So that's what the learning rate does. So now let's look at the exact terms of back propagation algorithm. So you basically, the concept of back propagation is used to learn the weights from multi-layer networks. Back propagation stands for back propagation of errors. What are you propagating back? Like when you take this thing and you're saying I'm doing back propagation, you're propagating the error back. So that's why it actually says that it stands for back propagation of errors. Given a network with fixed architecture, you basically take the error and then propagate it back to the weights of each of the neurons. So how do you actually optimize the weights? It's by concept called gradient descent. We'll actually see why gradient descent is used or how it is used in the next class. But this is what the gradient descent tells us. Whenever you want to find an optimal weight to minimize your error, you have to subtract it with some learning rate times that particular differential. So if you look at it, this particular component is telling you how much this weight is contributing to that particular error. So if your error is large, that means you'll subtract a bigger portion. If your error is small, then you subtract a smaller portion. That's what I said, right? The initial weights are what we guess, but after that we don't guess the weights because it depends. The update equation of your weights depend on your error. So if your error is large, then you update the weight using larger value of this. If your error is small, then you update it using smaller values of this. So let's actually look at an example. So this is all the things which I explained of how the update. So this is the training step or like how the back propagation goes. But I think the better thing is basically to show you an example of how this thing. And as I said, right, one epoch is one backward pass and forward pass of all the training samples. This is an epoch. So let us go and take a look at it. So everyone understands like what a neural network is and how the weights are, right? So now let us look at, okay. Now let's look at this thing. So this is my neural network. I have two input layers. I have two hidden layers. I have one input layer and one output layer. And these are the weights I have for each of the perceptrons which are connected to each other. So now my input data is, let's say I have 0.5 and 0.1 are my features. So ideally, I won't make the class label as 0 and 1 because it's very difficult to find something which is 0. So I make it like 0.01 as the label and 0.99 as the label. I do this on purpose because if you actually try to make it 0, then all the weights will actually tune themselves to 0, right? Then you can multiply 0 times 0 is going to be 0. So ideally what we say is instead of using 0 and 1 as the labels, I'll say my labels are 0.01 and 0.99, so that we don't run into the problem where all the weights become 0. So let's say, so now this is our thing. So let's say these are the weights. So let's say the algorithm randomly comes up with 0.15, 0.2, 0.4, 0.25, 0.3. So these are the random weights which it gets. Let's see how it go further. So first, what we do in the forward pass, we calculate the net, which is basically W1 times the first input, W times second input plus bias. So you calculate the net there, and then after calculating the net, what happens to the net? You pass it through the activation function. So in this case, when we use these values, we actually plug it into the activation function. You get the activation function, which is 1 by 1 plus e to the power of minus x, right? That's a sigmoid activation function. So you get that, and your output is basically from the first input vector, your output is 0.59. Is everyone following this calculation? So all I'm doing here is I'm taking random weights. My target value is 0 and 1, but I'm using as 0.01 and 0.99. And then I'm calculating for each input layer what is the output. So 0.5 is the input, 0.1 is the output. So these two are features, right? So I'm passing these two features to my hidden layer. So for first hidden layer, it would be 0.1 times 0.2 plus 0.2 times, so it's WIXI plus B. Is there any questions on this, the forward pass? So once you calculate the net, you have to pass it through the activation function. And the activation function for now, let's assume that the threshold is just 0. So it passes that thing further. Questions?
I just had another question that I should have asked before, but how do you know which activation function to use? I remember you saying that you're saying the tan H passes through 0, but yes. For other ones, how do you know which one to use?
I have one slide on that. So basically, so if you actually take this equation, right? So let me go back to backpropagation. So this is the update equation for the weights. So if you look at this equation, you're actually taking the partial differential of that particular error with respect to that particular weight. So if you actually calculate the error purely in terms of math, right? So the error will actually include this term, the activation function term, because the output is basically going to be 1 by e to the power of, if you look at this, so this particular thing is your activation function, right? So this particular activation function is going to be part of your error term, because the error is, what is your error? Error is nothing but your expected output minus observed output, right? Or vice versa. You can actually use observed output minus expected. So this expected is basically a constant term, right? Because the expected is 0.01 or 0.99. But this particular term, what your observed output is basically going to include 1 by 1 plus e to the power of w1x1 plus w2x2. So when I'm taking the partial differential of the error, with respect to certain weight, here I'm actually differentiating this function with respect to that weight. So that means that you have to take the derivative of this function. So one of the main things in deciding what function or what activation function to use is because then the activation function needs, so one of the criteria is the activation function needs to be differentiable. Because if you can't differentiate that, you have to differentiate the activation function. If it can, like, this is a mathematical property of that function. If it cannot be differentiable, then you cannot use that as your activation function. So one criteria, so all the sigmoid, tan h and everything, they're all differentiable functions. But if you look at the curve of tan h and sigmoid, so if you look at sigmoid's curve, like if you go here, so tan h is nothing but an extension of sigmoid because it passes through 0, and tan h does not pass through 0. Let's go here. Okay. So let's say this is the case, right? Let's say I'm using tan h as my activation function. Do you observe anything weird about this function? So what is differentiation, right? Differentiation is nothing but when I'm taking differential of this tan h function with respect to certain value, it's nothing but the slope, right? You must have learned in high school that the differential of a function is the slope of the line. So if you see the slope of the line, it is pretty constant from here to here. Like here to here, it is pretty constant, right? It's the same. But if you observe the section from here to here, it changes really fast. See the slope of this line, or the rate at which this function changes with respect to input is really fast here and here. So this is what a lot of people don't use tan h as activation functions now, is because of this thing. Because if the data inputs lie in this section, it is fine. But sometimes when you come to the corner cases, the differential is really high. So for a small change in the weight, you are seeing very large changes in the error. So the activation function there does not converge that well, as opposed to ReLU. ReLU is a pretty straightforward activation function. It is this. It's going to be 0 till it hits some value, and after that it's going to be linear. So it doesn't change. It doesn't change like this thing. The slope is always constant. So ReLU is really fast to learn because because the change of weights is going to because the slope is really high right here. So when you change a little bit of W, your error changes quite a bit, or the value, your predicted value changes quite a bit. So it is very difficult to converge in case of using a tan h activation function. But when you use ReLU, it's the slope is pretty constant. So it gradually changes and then converges to some value. So a lot of neural networks use ReLU. Is that clear as to why we are using ReLU as opposed to like these activation functions? That's because when you're doing the first step is when you're doing back propagation, you're using this particular equation to change your weights. This equation says that when you're doing a partial differential with respect to the error, this error function contains the activation function in your actual equation. So when you're doing a partial differential with respect to error, the rate at which the slope changes for tan h and sigmoid is really high at the corners. So therefore, your slope is really high. So if the slope is really high, then it is very difficult to converge to basically error 0. So error has to be 0, right? The reason you're updating the W's is so that your error becomes 0. But in case of tan h or sigmoid, the rate at which these corners, the rate at which it changes is basically really high. So in such cases, we don't use tan h, we use ReLU. So the criteria to determine activation functions is it should be differentiable and it should have pretty much a constant slope, or else your activation functions will not be useful. So is that clear? I forget who asked that question.
That was me, and it's clear.
Okay. So these are some criteria in which you actually determine the activation functions. So ReLU is picking up popularity because the activation functions becomes part of that differential, which we actually plug it to find the weights. And if the slope is really high for certain values, then your weight changes quite a bit. So as opposed to ReLU, which is a constant slope, therefore it learns it gradually. So that's why we pick ReLU as the activation function. Most of the structures these days pick ReLU, but there are some, because for other cases where you don't go into that range, right? Let's say if your input equations actually always lie in this range, then you can use tan h because the slope is pretty much constant in this range. But if it goes, like, you never know how your input equations vary, right? Input data varies, so therefore sometimes you might lie in this section, in which case the slope actually increases quite a bit. But ReLU function looks like this. It's a constant slope. That's why we use ReLU these days. Anyway, let's go further with back propagation. So is this clear? So what we are doing, we are taking the inputs. So these are my inputs. These are the values I got. I'm calculating the W net, which is W1 times. These are my random weights, which I first got in the first iteration. And then I calculate the W net and I put it into that output function, which is the sigmoid activation function, and I got this output. Similarly, I get the second output. So this is the first output for H1. This is the second output for H2. And finally, I get the output for, this is the final output I get after passing it through two layers. So first layer is this. So the output of this is again input to this. The output of this is input to this. So if I use the same activation function of sigmoid in both the cases, this is my output. But is this what I want? This is my output. But my output is, what did I say the output is? It's supposed to be the label. So label is either 0 or 1. In our case, we are using 0.01 and 0.99 because we don't want to make it completely 0. So what we will do in this case is first calculate the error. The error value which is basically given is because we don't want, we want to make the error independent of the sign, so we square it. So the error value is generally half of target minus output whole square. So if you take that value, so this is the error value. So you take the error value and remember what I said, like you need not have one output, right? Here I have two output functions, one for one for the label which is 0 and another one for label which is 1. So again, in this case, what I'm expecting is in all the 0 outputs will go into this particular, all the 0 labels will go into this particular perceptron, and all the 1 labels will come to this particular perceptron. So what he is doing in this case is basically calculating the error for each individual one and then summing them up. So you see, he's actually calculating the error from both the terms and summing it up. So then what we do is we actually do the differential. As I said, right, if I want to update the W5 weight, I take the total of the error total and then differentiate it with W5. So that again, so this is a little bit of math. We do a partial differential. So that translates to this by second output times first output divided by this. Because there's E2 doesn't have the W5 term in it, right? So you do a partial differential equation. So you need not worry about this. The neural network algorithm will take care of it. But I just want to show you how the update works. So you take a partial differential of that. The partial differential of that comes out to be 0.07. And then what you do is, so ultimately, when you do the partial differential of everything and then multiply it, you get this as your partial differential. So ultimately what you do for updating the weight is you calculate the partial differential of it and then you actually update it with this equation. The equation I was saying was every weight times certain learning rate. This is something which you provide. In this case, I provided 0.5 as my learning rate times the partial differential of error with respect to that particular weight. So you take that particular, so this is how we found that particular slope of that, and then you subtract the weight. You basically subtract the weight, and then this is your new weight. So earlier you started with 0.4. It said, no, that is too high. So now this is how you update the weight. So similarly, you update like W5, W6, W8. So everything gets updated depending on the error. The higher the error, higher is the change of the weight. So all of them get updated, and now you calculate it again. You plug it back in, and now you do a forward pass on it. So once you do that, you will see that the error has significantly reduced from last time. Last time we had an error of, what was that error? So we had a 0.29 error, and look at after updating the weight what the error is, 0.036. So as you can see that, so you can do another pass, and then it will become like even less. So second pass, if you do second time the weights get updated, this error is almost close to 0. So we can stop the updation at this point. So now you have learned, the machine learning algorithm or neural network has learned itself. So is this thing clear of how the backward propagation works and how errors, weights are updated and stuff? Any questions on backward propagation? Are you guys following what backward propagation is doing, how weights are being updated and stuff?
Yes, sir.
Okay. So like if you follow, I think there's a question on. Okay.
So is there any software to do all kind of calculation?
Yeah.
Like
So,
MATLAB or something?
No, we are using sklearn library. So we will do all this calculation. We'll actually train a neural network now. So in the code, so I have three examples where you have digit recognition and stuff. So we are using the package sklearn. Sklearn neural network is something we are using. It's called MLP classifier, multi-layer perceptron classifier. We will see when I come to the code and exercise. So you need not, again, so this is something for your knowledge. If you look at the code, again, all the code is like very, very simple code. So if you look at it, so all you do is, I'll show you what you have to do. So where is the thing? You first scale it. So all you actually say is create multi-layer perceptron, give it the number of hidden layers, like how many, I create 3 layers with 30 neurons each. You can give like how many neurons have to be present in each layer. You say fit, predict, and you give the number of epochs it has to learn, it will learn. So you need not worry about how these calculations are done or everything. Everything happens in the package itself. So we are not using MATLAB. That's why we learned Python, right? So Python actually has all these packages where you can just simply plug in whatever you want. Like in this case, I created 3 layers in which I changed the activation function. So I created one layer with 12 neurons and I use sigmoid. You can change your activation functions whatever you want. You can use ReLU. You can use, so that will be the exercise. Like you can change your activation function and see which one gives you the best. Which one gives you the best model for you. So the code is like 4 or 5 lines. If you see, the whole program is just this. So you need not worry about like the software which does this and everything. It basically is just like 5 to 6 lines of code. That's pretty much it for most of the cases. So all you need to do is just plug and change these parameters here. So you change these parameters here, like how many hidden layers do you want, what you need to train and stuff. And then the package will automatically do that. But this is just for your understanding, like how it is working behind the scenes. What does it mean when you're saying it's training an epoch? What does it mean by saying that we have these many hidden layers? So what is, like, each hidden layer is associated with each what weight and stuff. So that is pretty much on the back propagation, this thing. There is this, so we have, so we want to run neural networks. So I'm running it on 3 data sets. I want to give you an introduction as to what we'll do with the code. So the 3 data sets are, we're running it on breast cancer data set. So remember I told you like there are some packages in Python which will provide you data sets, right? So there is, sklearn has some default data sets. It actually has a breast cancer data set. So you load the breast cancer data, and then you basically, I will go through this when we go through the code. But there is one thing on breast cancer. The other thing is on digit recognition. So this is also part of like, so handwritten digits. There is a data set for digits in sklearn data sets. So you load the digits, you print out how many. So digits are basically a 10 class classification problem, right? It's not a simple 0 to 1. So now you actually have to feed in the data, and then each time whenever it sees the digit, it has to give the label which is close to what you are outputting here. So we will do that. And there's also this data which I wanted to like show you. There's this MNIST data. It actually has this handwritten digits. It has 60,000 examples and test vector of 100,000 examples. So this is a standard thing which people use for evaluating algorithms. So we can use even images to learn the data. So if you actually see, I have an example code on the MNIST dataset, so you can see how we process the image. It takes some time. Let it run. Here. So this is basically the number 5. So you can actually, I just wanted to display and show you like how each of them, this is the number 0. So how it is like, it's taking every pixel and learning that aspect of it. Anyway, when I come to the code aspect, we will see, but this is what we'll be running it on. So there is this data set called MNIST, which actually has, that's where we got most of our data from, which actually has this handwritten digit recognition. So we use different neural network perceptron layers and stuff to learn these models and basically see how, like what accuracy we get. So this is basically, it's an open question. You can change the number of hidden. So there is no one particular model which will learn the best. I actually used one in which I think I got around 70% accuracy. Whereas you can see that other models are like don't perform that well as compared to neural networks. So one thing which we can do is, I think one Sunday I'll give you this exercise. You pick one data set, use all the algorithms we have learned so far. Use KNN, use SVM, use decision trees, use neural networks. I will teach you naive Bayes and everything by then. So use all 5 of them, and then you'll see which one works best. The thing is, you need to fine tune these parameters for each algorithm. So unless you fine tune the parameters for each algorithm, you won't get like the best results. But then let's keep like a competition to see who gets the best results on the MNIST dataset. So anyway, we'll go through that when we are doing the exercise. What did I want to show? Yeah, so they're saying using neural networks is an art. Why do you say that? Because if you put too many neurons, you might overtrain the data. If you put too little, it's like how you put like salt in your curry, right? So you have to be very precise. So it's basically you need to pick number of neurons in each layer. So if you put too many of them, you might overfit the data. If you put too little, so it's again, there's no hard and fast rule. Like you know what the output is, you know what the input is. You should see that you should actually pick your neural networks, neurons and stuff such that you don't like overfit the data, don't overlearn. So, sorry, this actually ran. So this, you can see that each image, so I'm giving you what each layer is learning. Anyway, when we run the code, I'll show you that. But what is the learning rate parameter to use? Whether you should put them sequentially, whether you should put them like in parallelly. Like how do you design your neural network such that, so that's why it's not a straightforward thing. Whether if it was straightforward, then like maybe there's no use of us being there, right? The only value add humans are adding to this is to come up with the configuration which will solve the problem the best, right? So basically that's why they said using neural network is an art. So yeah, you can change a lot of things. You can change the learning rate, you can change the inputs, you can change the number of output layers, you can put number of hidden layers, you can change the number of neurons, you can change the activation functions in each of them. So you can play. So not everything needs to be one activation function. So I can take first hidden layer, use sigmoid activation function. Second hidden layer, I can use ReLU activation function. So you can see by changing activation functions also. So ideally, everyone is drawing decision boundaries. It depends on whose decision boundary works best for the test data. So, okay. Interpretation of hidden layers. So this is basically the neural network lecture on this thing. But now I want to go into like deep learning and stuff. At this point, let's actually take a break and write some code, because I think if I complete deep learning, I think I want to complete deep learning the next class. Next class we will see what the convolution neural networks are, how that works, how recurrent neural networks work, how like you check. So what is early stopping? What is active learning? So there are like a lot of concepts in this. I don't want to overload you with everything in one lecture. So next class we will see what convolution neural networks are, and we'll cover what gradient descent. So we've used gradient descent approach for back propagation. So this particular thing here, the way we update the nodes, is basically called a gradient descent approach. So the reason is this is the gradient or the slope. Descent meaning this is reducing it by the gradient descent. So slope you calculate and you're reducing the weight using the gradient, right? So this is called the gradient descent. We'll cover one whole lecture on gradient descent, and we will continue with convolution neural networks and active neural networks. So we have a couple of exercises on convolution, RNNs and CNNs. So instead of or do you want me to continue with that right now, or do you want to just do an exercise on the basic neural network so far?
We can do one exercise.
So let's do an exercise. So actually, I want you guys to code this, because it's again this. So you can reuse the code from last time which you have written. So if you look at it, the code is really, really small and really simple. So the things which you need to do is you load from sklearn library. First, load these data sets. So let's run an algorithm for breast cancer. So there is this breast cancer data set available in sklearn. So what you do is you create a sklearn data set, you import breast cancer data set. In model selection, again, so this is something commonly we are using. I won't explain this again. So we actually use this test train split to basically get the data and split the data. We generally use 70-30 ratio. You can see here. So we take 70% as test set, training set, and 30% as test set. And then we use, remember I told you have to scale the data. So it's part of the pre-processing. So sklearn pre-processing has something called a standard scalar. The reason being, we actually have to normalize the data between 0 and 1. Every feature has to be normalized between 0 and 1, right? So that, and then there is the neural network is called MLP classifier. MLP classifier means multi-layer perceptron. So we have one perceptron, we have multiple layers of perceptron. So multi-layer perceptron classifier is our algorithm, and then we print out the confusion matrix. So let's go through the code, this thing, and I want you to code this. So this is the basic multi-layer perceptron algorithm. So once we cover deep learning models, we will go and do the rest of the exercises for digits and Indian liver patients. But so steps in this: first, you load the breast cancer data. You can, if you want, you can print out the keys. Keys will give you the number of classes in it. You can, so this is again nothing but a data structure, right? Data frame. So you can print out its shape, you can print out the data, you can print out its target value. So from this, I'm just using the data frame with columns data in X and the target value in Y. And the usual, like we did last time also, we take the data, we split it into test and train. Again, we do it randomly. So we put 30% in training and 10% in testing. I just printed out the number of observations. but this is one thing which we do prior to that is basically we do min-max normalization. What that means is we basically take the highest value and give it 1 and the lowest value and give it as 0. And then we create the standard scalar normalization thing. We first fit that particular, so we pass all the data to this to the normalization function, and then we actually transform it. So basically the transform actually transforms the features which are really high in number to like between 0 and 1. Similarly, you transform X data and Y data. The labels you need not transform because the labels are always 0, 1, 2, 3. And then you fit this multi-layer perceptron, fit it with, I've created 3 layers. It's up to you how many layers you want to fit. You can create 20, 30, 40 and stuff like that. And you can then fit the model and then predict the model. And then you can print out the confusion matrix to say which one is working better. So this is a very simple thing in which I'm just creating 3-layer perceptrons. I'll show you the next example how you can change the activation functions in each layer and stuff. But let's quickly write this code. Main thing is, I think last class you guys have written the decision tree code with in the class, right? So it's pretty much the same format. All you need to have is basically in this case, one thing is additional thing is nothing but the standard scalar. The standard scalar actually scales the input feature vector in between 0 and 1. So if you have the input feature vectors, you actually map it between 0 and 1. And then you create the MLP classifier algorithm. You can play around with the number of hidden layers and stuff like that. So every time I teach you any algorithm, right, you can just query this in Google, MLP classifier. You'll get its documentation. So for now, I just am using hidden layers as the parameter, but you can change other stuff also here, activation functions and stuff like that, which I have done in the next class and in the next exercise. I'll show you how to change the activation functions and stuff. But just for getting started on like multi-layer perceptron classifiers, just start writing this code. And then we can, if you have any questions, you can ask me. So I'll give you like 20 minutes to load the data. So this is something, wait, is this clear? Like we have been doing this for almost like four classes right now. We are loading the data set, splitting the data set into test and train. We are creating a model, we are fitting the model, predicting it, and then we are classifying it. So the coding aspect of the neural networks shouldn't be, or any machine learning algorithm should not be something new for you right now. It should be by default. You should actually have this on fingertips. What we are doing, how are we testing the data, how are we splitting the data, how are we using predictions on the data. So this should be pretty straightforward by now, because we, like every algorithm, we're following the same routine. So why don't we quickly import the multi-layer perceptron classifier on the breast cancer data. Let me know if you have any questions. So I'll send this code either ways. So you have it with you, but like just get into the habit of writing this. So all the new thing what you're doing here is creating a scalar, standard scalar. You're fitting the data to it, and you're transforming the data such that your X train and Y train data is normalized. And then you're creating an MLP classifier with 3 layers with I use 30 neurons in each of them, but you can change the number of neurons. You create that, you fit the data. You fit on training data, right? And then you predict on training and you predict on test. The reason I'm doing prediction on training is so that I know, because I'm I'm fitting from training data and still predicting training data because I don't want to overfit it. If I have 100% accuracy in training data, that means I overfit the data, right? So ideally, you should only use it for testing. So once you learn it, once your model learns, you actually use it for the test data. And then you use the confusion. How many of you are writing the code?
Writing the code.
Yeah, I encourage you to write it so that you get you, because if you don't write it, right, like you can obviously take the code and run it and then go through it, but you lose the habit of coding it in Python. What is the purpose of transformation? So remember when I told you initially that whenever you're giving the data, the reason we need to transform everything to 0 to 1 is because if you look at the Indian liver patients data, see there is one section which is basically age, which is varying between 65 to maybe like 22, and the other one is bilirubin count, which is varying from 0.7 to 1, right? So now imagine, like, if I change a little bit weight on this thing, so this is the variance and this is like in 0.1 to 0.3 or something, but the age, if I change by 5, your weight will basically this feature will contribute more to it, right? Because it's delta of 5, but whatever the maximum delta here is like maybe 0.5 or 0.3. So you have to normalize the data first. If you don't normalize the data, that means each feature, there are two reasons we need to normalize the data, right? Because each feature should be of equal importance. You cannot basically take age, and because age, the variation in age is really large. But in this case, if you actually use if you don't normalize the data, then each feature is given different weightage, right? Because any change here is of the order of like 5 to 10. Any change here is like 0.1 to 0.2 and stuff like that. So basically, that's the reason we normalize the data. Sorry? Hello? Sorry, was there a question? I thought I heard a question. All right, I'll give you like a few minutes to run this code. Then we'll continue with it. I'll just get some water. Huh? Just I'll be back in 5 minutes. I am back. Did you guys finish the?
Sai, for reference, can you just go down? Like,
Oh. Why is this thing? You know what? I'll actually copy paste the code, but I think I'll send this code anyways. But paste it. So the main thing here is this MLP classifier function, right? So MLP classifier, you can actually change number of hidden layers. So there are different packages. I think I have to, maybe I'll take a second here to talk about the packages. So most of the stuff which we have done is using sklearn library in Python. So there is other libraries too. So for example, I've done another, so I've used Keras also. So Keras is another model which you can use to actually, so I mean, there are different packages, right? So Keras, sklearn, and these are the popular ones in Python, which actually you can use for training and testing. So Keras is another model in which you can write this algorithm. So you can actually, Keras is especially for deep learning. So they don't have anything else, like they don't have other algorithms. So in Keras model, there's sequential and there is parallel models, which basically are nothing but neural network models, in which you can create different dense layer functions and stuff. So most of the algorithms which we did so far are from sklearn. We will, but I wanted to introduce Keras because if you're actually going to learn deep learning, we won't be doing deep learning here because that is an advanced topic, like where you can use convolution neural networks, RNN, and stuff like that. But most of the people who work on deep learning work on Keras data model. And then this is a simple, I didn't want to create a complex deep learning model, but there's one example I have here, which I used for Indian liver patients, in which I used Keras deep learning model. Then there's another thing which I have for digits, the handwritten digits classifier. Again, that's also based on the standard MLP classifier, in which I actually used different set of hidden layers. So instead of using 3, I used like 150 and 100. So I increased it by a lot. You can see the change in the training time and stuff for that. So anyway, I just wanted to tell you that sklearn is not the only one which you can use. You can use Keras also for training, like neural network classifiers and stuff. Any questions in the code, like what we are doing or how we are changing and stuff? Maybe as an exercise, I'll give you this thing. So using MLP classifier, not only you can change the number of hidden layers, right? But what you do is now try to change the activation functions for each classifier also. So that will be your assignment. Use different activation functions for each layer. Use ReLU for the last one. Use sigmoid for one of them, and maybe use tanh for the first one. So for each hidden layer, use different activation functions. And all these things, right? You have to basically go and look at MLP classifier documentation to see what additional things can be changed here. So I'm pretty sure you can even change the learning rate, the number of epochs. If you don't specify the number of epochs, it I think uses like 30 or 40 epochs. That's the default standards. But the things which you can change in this is number of hidden layers, number of neurons per hidden layer, number of epochs, learning rate, and activation function. The 5 things which you can play around with for neural networks are these things. Any questions on this? Deepika is still working on the...
Yes, I just 1 more minute.
Yeah, sure.
I'm done. Thanks.
So you can use the same template for most of the algorithms. Like, so all we are doing is splitting test train data, then we are fitting a model, and then we are predicting it. So if we actually increase the number of hidden layers, so I'll actually now talk about what exactly happens in a hidden layer. So it kind of looks like magic, right? We just right now just understood that, okay, we can change the weights by using back propagation and stuff like that, right? But if you actually see, there are, each layer learns certain portion of uh, of the given inputs data sets. A best way to a best way to see or learn what each layer does is, okay, wait, I'll wait for you to finish before I go and like talk a little bit more about hidden layers and what they do. I'll also talk a little bit about a concept called transfer learning. Transfer learning is a recent concept which people have developed, in which you can basically transfer the learning of one neural network into another. So that is something which has been popular very recently, based on what every hidden layer does. So let me know once you're done. Satya, are you writing the code as well?
I'm trying right now to write the code.
So what I would say is make a standard template, right, for all these codes, the standard template. So ideally every class, like whenever you write the code, there's just this you need to change. Ideally, I mean, in this case, we have the scalar transform, which normalizes the data, but everything else is the same because we do the confusion matrix for everything. We do the test train split for everything. We actually, we segregate the data for everything, right? So ideally, this is what we need to change.
Okay.
So because it's, if you're doing scalar, but I'll also teach a model with Keras. So Keras is something which, Keras is especially, so sklearn is a general library for machine learning in Python, where we can do like these different classification algorithms and stuff. But if you actually, Keras is basically only used for like, uh, Keras is mainly used for deep learning and neural networks. So Keras is something which, I mean, if you like, because a lot of work has been done only, I mean, in the deep learning areas and stuff. So there's a dedicated library only for deep learning, which is the Keras library. But in general, you can actually, if you want to like play around with different algorithms and classifiers, we can actually learn. We can do it using sklearn also. So Deepika will take this offline because
Yeah, sorry. Yeah, we can just do it later.
but
I'm just running into some typos and some other.
yeah. So because I mean, if there are no major questions in this thing, because we have little less, I just want to cover what hidden layers do. So we've seen that we are changing the number of hidden layers and stuff, right? In each of the in each of this thing, we are changing the number of hidden layers for like, so this is the hidden layer, right? So like I'll just talk a little bit about hidden layers, and then I'll talk about what active learning or transfer learning is. So in general, right, if you look at wait, do I have an image of that? Let me check. No, there is no image. But if you actually look at images, right, like for example, let's say face recognition. In so hidden layer is learning something. We don't know what it is learning, right? Like, so let's say we have 4 hidden layers. We have input layer, 4 hidden layers, and then 1 output layer, right? So the hidden layers is basically the more information you add to the hidden layers, it's one more additional uh, decision boundary you're actually adding. But some I don't remember who, but they presented a paper on this MNIST, and then what they did is they dumped out. So if you look at this example I have for MNIST, this thing. In this, what I have done is, so here is where actually I've used most of the other stuff. So I told you, right, MLP classifier does not only have hidden layers, it has number of iterations, it has learning rate. You can change a lot of other parameters using the MLP classifier. But anyways, so what it does is, let me just run this. So this is basically digits, but I think a much better understanding you'll get from hidden layers is through face recognition. So what they did is they printed out the image after each hidden layer did. After each hidden layer, so they actually dumped out the images what it learned. So what they found is because these hidden layer are learning the inner state of a particular problem, right? Let's say if I take a face recognition, for example. So what they found is one particular layer is learning the shape of the noses. Another particular layer is learning the shape of the eyes or the contrast in the eyes, the color of the eyes. Another particular layer is learning maybe like the shape of the face or like ears and stuff like that. So it depends on like, so each hidden layer is actually learning certain portion of the image. So what someone did is they actually did a concept called as transfer learning. So what transfer learning does is, let's say if you have let's say this Microsoft trained a really high convoluted neural network, right, which actually went and learned different shapes. So it basically learned shapes. So it actually worked on different areas where it did a classification of horse with car with basically bicycle and stuff. So in this concept called active or transfer learning, so what they realized is each particular, like for example, in this case, if you see, each particular neural network layer is learning something, some different aspect of the code. So what they thought is, if we are using a general classification, why don't we just take why don't we chop the neural network such that we take like 2 hidden layers from this network and then put it to our network, give that as an input to our network. So so what they're trying to do is that if half of it has learned about the shapes, like let's say if someone learned about like the nose and this thing, and let's say you're using some other data set, you need not, because maybe your training data set is not that large, but let's say Microsoft has access to maybe like million images, and you have access to only 100. In your 100 images, 70 if you learn, and then 10, 30 if you test, you don't have much data, right? The neural network is not learning much. But how about if Microsoft also ran it on like 1 million images, how about I actually take like 2-3 layers from there and then connect it to your neural network. So you already have layers which actually learned the shapes really well, right? So that concept is called as transfer learning. Transfer learning means you're transferring the learning of some other neural network which has been run on a similar problem. Like let's say if you're doing an object classification problem, so you basically take some other neural network which has learned on a much larger database, because the main thing is the training time, right? So if you basically have 1 million images, for you it will take like infinite time for on your computer to actually run it. Maybe it'll take like 4 months. You can't wait for 4 months for your network to train. So what people are doing these days is they're transferring the learning of the hidden layers of other complicated neural network because they're already learned, and then they plug it into your network and then they use that particular learning from those networks. So is that clear, like what they're trying to do? So that concept is called active learning. So let's say let me just share this thing. Make clear. So what this concept of active learning does is, so let's say you have, so this is your inputs, right? You have one layer where you input all this thing. You have one hidden layer of perceptrons, another hidden layer of perceptrons, and then you have third thing. So they're trying to see what each layer is learning. If each layer is learning something else, like in this case, let's say if one layer is learning about the nose structure, right, and another layer is learning about like the eyes and something like that. So they are saying that, okay, we'll take these two layers and plug it into my algorithm, because this has been trained on much larger data set, right, instead of me learning the data set. So ideally it is very difficult to find out what each layer is learning, because for us all, a neural network is a black box, right? We cannot basically dissect it open and see what each layer is learning. But if you have some other network, so this has been really popular. This concept is called transfer learning. You're transferring the learning of some other network into your network. It's the way to think of it. It's not humanly possible, but let's say if you have someone who's way smarter than you, right? You can take certain portions of his brain and put it in your brain. The idea is you will get smarter, but that's what you can do in this case. So that's what is basically they're trying out. This is a new concept, which is like it is like last 6 months to 1 year, it has become very popular. It's called transfer learning. So where you basically transfer the learning of other hidden layer networks into your networks, and then see if it is performing better. So having said that, I don't want to start with deep learning today. Not deep learning as such, but I will cover a little bit of convolutional neural networks and recurrent neural networks in the next class. So these are like deep learning models. So what we did so far is like the basic neural networks. So how backpropagation works, how each of them work. But when you expand this to a really large number of neurons and number of hidden layers, and use different hidden layers to actually use different hidden layers to solve different problems, we'll talk a little bit about that. So convolutional neural network actually is one of the deep learning models where you have a pooling layer and a convolution layer and a connected layer. So we'll talk about what that does, and there are like other recurrent neural networks also, in which LSTMs, or it's called so recurrent neural networks use something called as long-term short-term memory model. We'll talk about how those work. I'll just give you a brief overview. I won't go into the details of it, but these are the other things in neural networks which are there in the current state of the art. So the exercise for you is just play with the multi-layer perceptron for this time. When we talk about deep neural networks and stuff, we'll do Keras. So Keras models and what Keras does, we will talk in the next class. And we will do gradient descent. We have a whole lecture on like how gradient descent works. So after doing gradient descent, when we do linear regression and logistic regression, you will understand that much better. And when we do that, but we'll finish off with neural networks. We'll do gradient descent. And the next Sunday class, we will do random forest and boosting, especially AdaBoost and XGBoost. So that, and next Wednesday, I thought we will do naive Bayes. And next to next Sunday, I'm thinking we will not have a class, but we'll have an exercise session where you get to like use, just take in all the algorithms you've learned so far and run on one data set and compare the results. So that would be a break, because after that we'll start with R. So we'll do R, and then we will we'll learn R models, and then we'll do linear regression and logistic regression in the last few classes. Is that clear? Any questions so far, or anything from until? So don't go into deep learning yet, but what hidden layers are, how perceptron works, what backpropagation is, what activation functions do, how do we choose activation functions, why is ReLU being more popular than sigmoid, and it's actually, that is an interview question. Like I've seen a lot of people ask, like, why are you using ReLU as compared to like sigmoid and tanh. The reason being, sigmoid and tanh actually at the corners have a higher slope. Therefore, changes in the any change to the error function there is going to result in a much larger variations in any change in the weight will result in much larger changes in errors. So therefore, as compared to ReLU, it's having a constant slope. So that's why people are preferring ReLU. Anyway, with that, I think I'm going to stop today's class.
Sai, can you send the code immediately so that I just want to
Okay,
double check?
I'll send this. The thing is, right, for the video to process, it's taking like 2 to 3 hours. That's why I was sending it the next day. But I'll send the code right now, and maybe I'll send in another email. I'll send the.
Okay, yeah, thanks.
And I'll send the video.
Thank you.
Okay. Okay. Any questions or any other things which you guys want to discuss? Okay, if not,
we will have class on Wednesday, right?
Sorry?
Next class.
Hey, we have
next class we will have.
We have Wednesdays, and then we have on Sundays. I'm saying not next. I'm saying next to next Sunday we'll take a break, because after that we'll start R. So before we start R, I thought instead of a class we will do an exercise with all the algorithms which we have learned.
Okay.
So we have class next Wednesday, next Sunday, again next Wednesday, and after that we'll take a break.
Okay.
Okay then. Okay, have a good rest of your Sunday. I'll see you guys on Wednesday.
Thank you.
Okay, thank you.